Good morning, good afternoon, good evening. Welcome to Flat Earth School, the school that is around us 24/7 since the beginning of existence. I'm Mitchell from Australia, merely a student like the rest of us, always learning, always questioning from our amazing teacher, the best teacher you could ever hope for, the Flat Earth School. Like I said, around us 24/7 since the beginning of existence. If you like my work, if you want to support my work, please hit the like, subscribe buttons, share the show. You can follow the links in my description boxes below. You can donate to PayPal, sign up to Patron, purchase my wife's beautiful book, ABC Pregnancy, selling like hotcakes. Thank you all very much for the support we've been receiving for the past 3 months. I hope you enjoy my work. All right, let's get straight into it today. So before we get into measuring a geometric flat plane, which has definitely been 100% proven to be where we live using the sextant, I'm just going to do a bit of a follow-up video on something that we saw last week from Anthony Riley, Sleeping Warrior, doing a bit of a experiment, if you will, about relative density disequilibrium. So let's just hear what the premise to this is. Ah, crap. Being told there's no sound. Thanks for setting me up, Anthony. Far out. Been playing that for a couple of minutes without any sound. Apologies, guys. Is there sound from my microphone? Hopefully there is. Adam Meakin, how are you? Michael Kahn, how are you? Yeah, fantastic start to the show. Would be great if there was some sound. Guys in the chat, is my microphone coming through? Testing 1, 2. Is this thing on? So anyway, that was Anthony Riley explaining that he has done an experiment with the egg in a medium, and he has, so the video had no sound. So he was showing that the cause to the egg moving was the manipulating the density around the egg. Let's see if we can pull this up and get some sound out of it. All right, so that's. We'll go back to the start. See if we can get this working. Crap, apparently still no sound on the video. All right, Anthony, haven't figured it out yet, but Anthony's saying that the displacement from the egg is due to the density of the medium around it. And so what is the opposing claim, if you will, to this is incoherent dielectric acceleration. And so what Anthony has done is hooked up, fast forward a little bit, he's hooked up a 12-volt battery into this, the medium, to see if any sort of electricity is going to cause any sort of movement in the egg. And he's turned it on, and obviously there was no movement from the egg. Now, this may have been tongue-in-cheek, but this is just a bit of a kick for the people on the incoherent dielectric acceleration side to get their stuff together and to do an experiment. Put this through the scientific method, because that's what Anthony Riley has done to prove the cause of the egg moving, manipulating the medium. That's what the cause of the egg was moving. And if you want to, this is solely a flat Earth argument here, on the side of the flat Earth. This is nothing to do with the globe, nothing to do with gravity. That doesn't come into this. That's been disproven. So on the side of incoherent dielectric acceleration, you guys need to catch up. You need to science what you think is the cause to the egg moving. And we'll leave it at that. At the threat of having no sound in the video again, sound is on. Oh, fuck's sake. Seriously, guys. All right, let's get into the actual presentation of what I was actually going to do today. So measuring a geometric flat plane. Okay, so yesterday we had a claim from the globe side. Before I get into that exactly, we had a claim that of a new radius from someone who has given us a radius value before, for someone who thinks that he has measured a radius value. It's definitely not the start to the show that I wanted, but anyway. All right, here we go. This bloke again. Yeah, let's see what he has to say. So, yesterday, I was saying that we don't actually have a radius to the globe if it's an oblate spheroid. Let's go through what I said. Hopefully the sound on this video will come through. Let me know if it doesn't, guys, in the chat, please. It is not available to us. Maybe it's because of the equatorial bulge, do you think? 27 miles wider at the equator? Now, this throws a bit of a spanner into the works, doesn't it? If you've got one radius of Earth being 39, 59 miles, what happens at the equator when you're 27 miles wider? So are you telling me, globe believers, that you can derive a radius value when you don't have one single radius value on your globe? It's an oblate spheroid, 27 miles wider at the equator than the poles. So why are we always told that we have a radius of your globe?
Is he serious here? Is this a genuine attempt to debunk the globe, or is he joking? Sorry, before we carry on, I forgot this bit.
That one has never been calculated or measured, begging the question. And two, it can never be calculated or measured because you do not have one radius. If it is an oblate spheroid, if you take a step, that is a different radius to your presupposed spherical Earth than when you took the step backwards. When you're traversing the globe, you've got a different radius at each and every point.
Well, Mitchell, it seems you've made a straw man.
Thanks, Wally, for confirming your understanding.
The problem is the globe side all know the radius is a maximum of 6,378.137 kilometres, according to the WGS 84, and a minimum between both poles of 6,356.752 kilometres. Now, Wiki claims these have been widely used in geodesy because they are accurate to within 0.5 of a millimetre on the Earth's ellipsoid. Gee, that's not bad going. Now, we actually account for the variation of the radius by, well, look, it's a bit in depth. How about you go and look up Thaddeus Vincenti? He is one smart dude, and I'm pretty safe in saying that this is way above your pay grade, Mitchell. Way above. Way, way above. How far above? Yeah, 10 to the minus 17 torr is about the pressure when we're that far above Mitchell's pay grade. So, Vincenti, he busts your straw man, mate. Sorry about that. We all know the radius varies depending on your latitude.
What was that? We all know the radius varies depending on the latitude. That's exactly, except for the latitude, what I said. The radius of your globe varies. What was the straw man here, Wally, that you just confirmed?
We all know the radius varies depending on your latitude.
Far out. Are you serious? This is the type of people that we are dealing with here. I've specifically said, give us a radius value. Give us one radius value to your globe, 3959 miles. Can you do that? Can you give us the specific heliocentric narrative radius value of 3959 miles? And here is Wally saying that it is not possible.
We all know the radius varies depending on your latitude.
So what has he calculated previously? What was he calculating when he was going through all the maths, going through all the calculations? I'll pull up the little image of when Wally claims to have measured the radius of the Earth down to 2% error. Here it is here. Remove that. There we go. Pointing at 2% error there. 2% error of what, Wally? You have just told us in no uncertain terms that the radius varies depending on latitude. So what is the 2% error to?
We all know the radius varies depending on your latitude.
So there's no one radius of 3959 miles. This is what we have just confirmed. So why, Wally, why do you keep saying that there is a radius? One radius to get a 2% error to? These are the kind of people that we are dealing with here. We ask them to just verify their religion, verify their story. And what do? They go and throw it under the bus. They go and blow it up beyond all recognition. This is what we've been talking about since the Black Swan. What is the radius of your globe? So apparently we have a maximum and a minimum radius for their globe. And what would the maximum be now after this Black Swan? 1.77 million miles. That's the new maximum radius to your globe. So thank you, Wally, for confirming that at each and every point of your globe, if you're begging the question, you're living on a globe, you have a different radius value. That's exactly what we have been saying here. Show us your radius value. Thank you for confirming that you have no one set radius value of 3959 miles. Now it's just a bit of fun, just a warm up to get into the real topic at hand. Measuring a geometric flat plane. And this is going to be very triggering and very devastating for globe believers, because that's what we're doing when using a sextant, measuring a geometric flat plane. So let's go through how we measure a geometric flat plane. Well, firstly, you need to use something like a sextant, an angle measuring device. But that's not specifically measuring the geometric flat plane yet when just using the sextant. There are some corrections you need to make when using the sextant, because when you take a reading with the sextant, you're getting an angle, and the angle is to the horizon. That's what you have to use. You have to use the horizon with the sextant. That's just what we have to use. But when you're above sea level, when you're above the level of the geometric flat plane which we're about to measure, there's always going to be a dip angle. Now I just want to put up a few slides here that people think debunks the flat Earth. These are straw men right here. From an aeroplane, we can see a dip angle. Apparently this debunks a flat Earth? No. This debunks nothing. This just proves that we definitely have an angle, a dip angle, when we are above the horizon. Just another little slide here. Something that we are told disproves the flat Earth. A dip angle to the horizon. Nope. Just showing that we absolutely have an angle difference from the observer when we're at altitude to the horizon. And that's what needs to be accounted for when using the sextant, because the vertex, the vertice, it's not at the level of the Earth when we're using a sextant. It's always going to be above the level. As you can see here, we can clearly see that there is a differing angle to the horizon. So when we're up, this image here, so 365 meters above sea level, you can see from that level there that there is a different level to the horizon. That's because when we're looking out from an elevation, we're looking out at a different level to the plane below us. So obviously we have to account for that. We have to account for the differing angle that we're looking at because we're using the horizon. So let me put it in a celestial navigation term here. So we've got this boat. He's got a sextant. See the little sextant off the back of the boat? That's where he's going to be taking the measurement to the sun from. So he is above sea level here. So when he takes the reading from his sextant, looking at the sun, he's using the horizon. And he is above sea level. He has to account for the error that he's going to get when he's above the sea level. Because that height right there, you have to account for that. And that is in all manuals of the Sextants operation manual. That can't be denied. Because you need to bring that angle right there, that vertex, down to the level of the Earth to get a true reading. And when we bring it down to the level of the Earth, when we account for that height where the angle is being shot from, this measurement here, this physical measurement now becomes geometric. We're placing that firmly on the surface of the Earth. So that, I'll just go back to the previous slide. This one right here, taking the angle measurement from the ship at elevation. You have to account for that height. And when accounting for the height, you're placing that measurement firmly on the surface of the Earth. And as you can see, that measurement there needs an absolute flat baseline. It is physically measuring the geometric plane that we dwell upon. To have that 90-degree angle there, it needs to be a flat surface. And we are measuring that with the sextant when accounting for the dip angle correction. This is measuring the physical geometric plane that we live on. Now I'm going to go through some references. Don't just take my word for it. So these are references from, anyone can look them up. This isn't new stuff here. Let's see, well, we've got celestial navigation. All right, so celestial navigation with the sextant. So there are a couple of things that we need to adjust for after taking a reading with the sextant. We need an index error correction, and that's just to do with the mirrors. And we also need to account for the dip, the height correction. So if you're taking your sextant readings from the bridge of a ship, as I just showed in that diagram, then you're going to get a different sextant reading to if you were on a small yacht, and obviously if you're on the ground. Therefore, we need to make a correction on what your sextant says to get your reading converted to a sea level reading. This is called dip, or an adjustment for your height of eye. Exactly what I just went through. Take a look at the table below. On the right-hand side is a column called dip. Imagine if you were standing up on the side of a small yacht when taking your sextant reading. You are likely to be about 3 meters above sea level. If you look down to the table until you get to 3 meters and then look across at the numbers beside it, you'll see 3.1 feet. This is our dip figure. And it is always subtracted from the sextant reading. That's what you have to do because you're always going to be above sea level. You always need to account for the dip angle. Now, don't get us wrong, ballers. This is not a tangent to the surface of a globe when we're looking at the horizon. There's so many things wrong with asserting that this is happening on the globe. Number one, do you have a straight line from your observer to the horizon if you're claiming refraction with the black swan? No? Bendy line? Number two, when you are accounting for the height, the dip correction, are you putting that flat level baseline that you don't have in the first instance on a curved surface of your globe that doesn't have a radius that we just went through? Yeah. Any claim that anything is happening on a globe is begging the question. That's why I started with the premise of prove that you have a radius. And Wally, thank you, Wally, has just proven that you do not have a radius to your globe. Everybody knows that the radius varies with latitude. Yeah, thanks, Wally. Remember I told you in no circumstances give a flat earther a soundbite? This one's a great kick in the pants for the globe. Thank you, Wally. Anyway, back to what we're actually doing with the sextant. So you need to put the dip correction into the table and combine the index correction with the sextant altitude to get HA, or the total apparent altitude. So hopefully there might be sound in this video. Let me know in the chat if there is or isn't. Make it a bit bigger. Yeah, no sound in video yet again. All right. All right, so it's just, I'll just let it play out and I'll describe it as I'm hearing it. So you need to account for the height above sea level here. You need to account for that height of the sextant. So the height estimated above the sea level there was 2.3 meters. And you need to also account for the wave height as well. So you can, in this example, I think they put it at 6 meters. And so after estimating the height of these waves, if there are waves, you need to take a reading from the top of that wave. So you estimate the height of the wave here. They said 6 meters, you half that. And when you get to the top of the wave, you take a reading. And that's another correction you need to make. So using the nautical almanac, you go through and you see the dip angle correction that needs to be accounted for when determining your height above sea level. So you go down the table and it tells you if you're at this height, you need to account for this in your sextant reading. So if we said 5.3, it needs to be put in the dip correction table there. There's a guy just using a sextant. It'd be great if the sound was on, but it's not. So these are the things that we need to account for. So we've got the sextant reading. Okay, that was from the top of the wave. 26 degrees, 18 minutes. And then you need to account for the dip correction, which is 4.1. And then you get the total apparent altitude right there. That's what you need to do in all instances. When you are above sea level, you're always going to be above sea level. No one is going to be in the water with a sextant taking a reading from that water. You're always going to be above the sea level, and you need to account for the dip. Because as we went through before, the dip accounts for your height above sea level. Just show those slides again. So obviously, we've got a 90-degree angle there from the celestial body to the GP and onto the flat plane. When we're taking a reading with the sextant, we're taking a reading from a height above the sea level. That's not disputable. We're always going to be a height above the sea level when using the horizon. Can't use the sextant without the horizon ballers. Absolutely must have the horizon as the flat, straight line in your measurement. But you need to correct for the height above sea level. And when you do, that brings that measurement down to the level of the Earth. And this is the geometric flat plane that you are now measuring. This is the killer blow here for the globe. This is the #1 flat Earth proof. We're using the sextant to physically measure the geometric flat plane beneath our feet. In all instances, when using the sextant, you need to account for the height above sea level. And when you do, it brings it down to the geometric flat plane. So let's go through a few other references. So that was this one, brilliant. All right, so this is the Mark III marine sextant, how to find your position with the Mark III sextant. We'll go down, so this is the index error correction here. So you set both mirrors at 0, and if you're seeing this figure here, two differing horizons, that means you've got an index error, and you need to account for that. So you turn the little knob on the barrel, and you line up the horizon so it's straight in both mirrors. That's the index error. And then you turn it vertically one way, turn it vertically the other way, to make sure that the horizon is absolutely flat in both mirrors, that they line up. That's the index error. That's one of the corrections you need to make. The other correction that you need to make is the height of the eye. When measuring the altitude of the sun, we want to measure the angle formed by a ray from the sun and a plane tangent to the Earth. There's that tangent, the radius that we don't have, that varies at every point of latitude. Thanks, Wally. So we want to measure the angle formed by a ray from the sun and a plane tangent to the Earth at the point where the observer is standing, due to the height of the eye of the observer. However, the visible horizon actually falls below this theoretical plane. So there it is, globe believers. Even if you think you're living on a globe here, you have to account for the height of the eye. And it's definitely not because we're living on a globe. That is begging the question. I've asked specifically for the radius of the Earth. And what did Wally say at the beginning of this video? We all know that the radius value varies with latitude. Yeah, thanks, Wally. So no 3959 miles then. No 2% error to the radius value. Yeah, you're definitely not doing this on a globe. But you definitely, regardless of where you think you live, you need to correct for the height above the sea level. So to correct for the height of the eye, one must apply a dip correction. Dip correction increases as the height is raised further above the surface of the water and must be subtracted from the sextant reading. So 5 foot or 1.5 meters height, you need to account for two minutes. So due to the height of the eye above the observer, the visible horizon falls below the plane tangent to the Earth at this point where the observer is standing. This needs to be acknowledged, globe believers. This is all references on your side. This is aiding the globe here. You need to account for the height of the eye to bring it down to a geometric measurement. Now, upon doing that, what's going to happen to your presupposition that you think you're living on a globe? Is that going to be a geometric measurement of your curved surface? No, you don't have a curved surface. And if you thought you did live on a curved surface, how are you getting a straight line from the base, from the surface of the Earth to the GP point of the star, or of the sun in this case? That figure that I showed before, that, put it back up on screen. How are we getting a straight baseline on a curved surface? Does not work. 90 degrees does not work on a curved surface, only works on a geometric flat plane. And that's what we're measuring. That's what we're doing when we're correcting the height above sea level after using the sextant. It is measuring a geometric flat plane. let's go back into the references, because that's not the only ones. These are some pretty interesting ones coming up now. The Nautical Almanac. So the Nautical Sextant, errors and adjustments, altitude correction tables. So as we said before, there's some instrument correction we need to account for. So this is just the index error. Went through before. Need to line up the horizons in both mirrors to get a good reading. And you also need to altitude measured with a sextant corrections to apply. So the dip or refraction, yeah, you can focus on that if you want, globe believers. Refraction. So if you're looking at the horizon, is that a refracted horizon? Is that a bendy line from you observing the horizon through the sextant? So no straight lines then. Anyway, so the dip, the error is due to the height of the eye above sea level. The dip is 1.7725 times the square root of the observer's height in feet. And notice this is different to the 1.22 because this is in meters. If it was in feet, so this 1.7725 times the square root of observer's height in meters. Have we heard that before? It is the same as 1.22 times the square root of the observer's height in feet. Doesn't that sound familiar? Possibly the geometric limitation to your globe believers, the black swan, the thing that we have absolutely debunked. The thing that I was going through at the start of this show, showing that what could the maximum radius of your globe be? This one right here. Yeah? When we put 1.22 times the square root of observer's height in feet through the Modus-Tollens argument, with the argument that we are living on a globe of 3959 miles, it absolutely debunks the claim that we have a radius. And when looking at the black swan, this is the new black swan from BMLSB69. Subscribe to him today. We're seeing from a 1.5 foot observer height. Plug this into the calculations. Plug this into the maths that proves things, ballers. 1.5 foot observer height. 31.82 miles to the horizon. The new radius. Yeah, where should the horizon be when using that calculation? It's definitely not 31.82 miles. The new calculation that we have for your radius value is 1.77 million miles. Yeah, we don't have a radius to your globe. That's what we're getting at here. Joe Kovac says, where is the semi-diameter correction on your references? Great question. And that is in one of the references here. That is another thing that we need to account for. Not sure if it's in this one. There it is, semi-diameter. So that was a question in the chat. Where is the semi-diameter correction? So it's the last correction, and it's only for the sun. The lower limb of the sun is used for solar observation. Therefore, a semi-diameter must be added to the altitude measurement because you're putting the sun on the horizon. So that's sun right there. Not sure if they're going to show it in this image. So you need to put the bottom of the sun on the horizon when using the two mirrors. And then you need to correct for the semi-diameter of the sun. And that's just another correction here. There's a few corrections that you need to do, and one of them being, yes, the semi-diameter of the sun. Another being the index error. The two mirrors need to be lined up. And one of the most critical ones, the dip error. Yeah, I was just going through this calculation right here. The same that we use in the black swan, Modus-Tollens. Isn't that interesting? And this is the correction table for the dip of the horizon. See that first one? 0.3 meters, about 1 foot. 1.2 nautical miles distance to the horizon. These are great. table here. Correction for dip of the horizon. This is from the Nautical Almanac. This is what we have to account for. Height above the horizon, 0.3 meters, which is about 1 foot. That's what you have to correct for it on the altitude that you read. And that's the distance to the horizon in nautical miles. Comes out to be about 1.225 statute miles. And what do we say in that correction? What do we say in that calculation? 1.22 times the square root of the observer's height in feet. It's the same in meters. 0.3 meters. Coming out to nautical miles. It's just different units of measurement, always the same calculation. So that is how we correct for dip to the horizon. The dip angle. Something that the globe believers, I don't know why, they don't like to bring it up. Unfortunately, Joe Kovacs didn't realize he was a glober. Yeah, you're going to need half of that, Joe. So let's go through a few of the other slides I've got here. Sharing screen. This is how we measure, physically measure a geometric horizon. Sorry, a geometric flat plane using the horizon. So this next slide is going to be from screen share. Window. Here we go. All right. Hopefully everyone can see this. Yep, should be on the live stream. This is from Nautical Science. Yeah, just disregard the science bit. Where is this? Here we go. Nope, not that one. All right. Next slide. All right, this is talking about using the sextant. And down the bottom here it says, so I'll just read most of this. An introduction to nautical science. Errors of this kind is called an index error. That's what they're going through. This is the errors that we have to account for. So good practice is to check a sextant for index error each time it's used, because it is easy for a sextant to be knocked out of adjustment from careless handling. A good way to determine the index error is to set the sextant to 0 minutes, remove all filters, look at the horizon. That thing that's out there, that we're using to disprove the radius of the Earth, black swan, looking at the horizon. So if there is no index error, the horizon seen through the clear glass and the horizon beside it in the mirror will form a continuous unbroken line. The sextant is measuring an angle of 0. There's that 0 angle. If there is index error, however, there will appear to be 2 horizons. So the reflected one will be either above or below the real one, depending on whether the error is positive or negative. So that's just showing that we absolutely need the horizon when using a sextant. There's no other way, or is there, to use the sextant other than the horizon. If in this case the micrometer drum should be, if this is the case, that you have 2 differing horizons with the 2 mirrors, the micrometer drum should be turned until the horizons are lined up as perfect as possible in one straight line. And then the angle read on the drum. So you need to account for that. That's the index error. It should not amount to more than a few minutes of angle. If it's much larger, the sextant mirror should be readjusted. It must be noted whether the drum has moved the index arm forward on the arc from 0 or backward on the arc from 0. This tells us if we must add or subtract the error from subsequent readings to correct the sextant. The rule to remember is if it's on, it's off. And if it's off, it's on. So this is index error here, using the horizon. Must have the horizon. It's the angle of 0, the first error correction that we need to be doing. So which means that if the error is forward on the arc, then we must subtract from any angle measured by the sextant and vice versa. So this is the first correction made to H. The next thing we must account for is the fact that the horizon that we see is not really 90 degrees from our zenith or from the vertical, unless our eye is right at sea level. Remember that image I was showing at the start of this? The 90-degree angle is to the surface of the Earth. So the eye needs to be right at sea level, and we need to account for that. So at sea level, the horizon is tangent to the sea surface and a right angle to the vertical. Isn't that interesting? But as our height of eye gets greater, higher, the visible horizon dips lower and lower. The higher our eye, the bigger the amount of the dip angle. So dip is purely a function of our height of eye. There it is right there. Dip is purely a function of our height of eye. Nothing to do with a globe, nothing to do with curvature, nothing to do with the horizon dipping away from us. No, dip is purely a function of our height of eye, right there in the reference. Dip is purely a function of the height of our eye. So if that height is known, dip can be calculated. And we've seen the table in the Nautical Almanac. That's what I was showing before. Put it up again. That's what I've been saying the whole time. That the 90 degrees is to the surface of the Earth. And when we're accounting for the surface of the Earth, when we're accounting for the height, we are putting this measurement solely onto the surface of the Earth. This is a geometric measurement. We're measuring a geometric flat plane. All right, so we'll go back to these references. So this is from Reed's seamanship. And these are just a few definitions. So vertical at the top here, perpendicular to the sensible horizon, straight up and down. Horizontal is perpendicular to vertical. Perpendicular is a right angle. Like these are just simple things that you learn in kindergarten. A right angle is an angle measuring 90 degrees. These are just things that we need to go through because the globe believers are denying these things. Where am I getting this from? Reed's seamanship. All right, you can go and look this up yourself, not making this up. So altitude is the height. And the arc, part of a circle. Not part of a sphere, part of a circle. Angular measurement or angular distance, the arc which measures the angle. Isn't that interesting? A 2D circle, a 2D arc. Sort of like an area of equal altitude, circle of equal altitude. So zenith is the point in space overhead. The radius, obviously half the diameter. That's what we're using when calculating the distance to the GP. Plane, that's a good one. Here we go, plane, flat surface. Great definition. The thing that we're measuring physically here, a plane, a flat surface. Isn't this beautiful? I'm not sure what the next slide's going to be, so bear with me. Oh yeah, there's these ones. So that's why we have to adjust for the height of the observer, because we are at a different height, so we need to adjust for that. Not on a globe, on a flat geometric plane. To bring that measurement from the sextant down to the surface, we need to account for the height. And upon doing that, it becomes a purely geometric measurement. We are physically measuring the geometric flat plane that we dwell upon. And also, did you catch that the 90 degrees, the zenith above your head, is from the surface of the Earth as well? And it's also another 90 degree to the surface of the Earth from the GP. And these vertical lines are parallel. Just adding, just piling on the evidence that the proof that we live on a geometric flat plane. You must have 90 degrees from your zenith to the surface. You must also have 90 degrees from the GP to the surface and the star. And obviously, this is making two 90-degree angles, and that line from the GP to the bottom of your zenith, the 90 degrees to the surface of your zenith, is absolutely flat. We are living on a geometric flat plane. It is physically been measured. It's game over for the globe. All right, so what we got? We've got about 9 minutes, guys. Just looking through the chat. Thanks everyone for turning up. Hopefully this has been enlightening for some people. Tomorrow, my special guest will be Brian from Brian's Logic YouTube channel. Check him out. Should have put the link in here. Brian's Logic will be joining me, and we're going to be going over these points. We're going to be hitting them hard, because these are the points that absolutely shatter the globe, that absolutely prove that we're living on a geometric flat plane. You can't get away from this, ballers. I don't know why, but they don't like to bring into account the height above the surface of the Earth. 10th Man says, Reed's quote was for seamanship and competency. Thanks, 10th Man. Gadget Inspector, how's it going? I'm going great. There is never a better time than to be a flat earther than right now. It is absolutely glorious. Never a better time to be a flat earther. And after this stream, head over to Quantum Racer's channel. He is doing a live stream after this. Always good content. Now I think after that, Nathan 1980, subscribe to those two channels today. Quantum Racer channel, subscribe. Nathan 1980, Nathan Oakley 1980, subscribe. Flat Earth Debates, got an uncut and after show after that. So I hope everyone's enjoyed this presentation today on how we physically measure a geometric flat plane, because that's where we live. There's no denying it. The sextant proves it. If you feel like the world turns on you, turn to Flat Earth School. It is around us 24/7 since the beginning of existence. All you need to do is just get out there. You need to see the world for what it is. You need to realize that there is no proof of any globe. You would never come to the conclusion that you're on a curved surface, that you're on a globe, if somebody didn't tell you. That's the only way that you're going to come to that conclusion. That's what they do in schools. That's the indoctrination. That's what they do on TV. You see, especially here in Australia, you see all the children's programs. TV is the biggest mind control, other than social media, other than media in general, just in general. But for children, what they're exposed to, the first 5, 6, 7 years of their life, they are so impressionable. And that's why there is so much globe propaganda in those children's programs. They would not come to the conclusion that they are on a curved surface without being told. That's why they get told. That's why they get bombarded. That's why they get sent to school to learn about the globe. Have that globe just sitting in the classroom. That's where we live. Have it in their programs. Oh, look, space. What's that beneath our feet? A globe. This is indoctrination. And it carries from childhood all the way through life. Unless we are actually realizing that the world around us, it is a flat earth school. It will teach you all you need to know about your world that you live in. Don't listen to me. Don't listen to the media. Don't listen to the experts. Go out into the beautiful flat earth school around us and learn these things for yourself. Be skeptical. If you think you live on a globe, be skeptical. Prove the globe to yourself. That's what every flat earther has gone out to try to do. Prove the globe to yourself. Because upon trying to do that, you turn into a flat earther. It is as simple as that. Yes, 10th man, dip correction destroys the heliocentric model. Absolutely, and thank you, 10th man, for this information. 10th man, a regular guest on the Flat Earth Debates, regular panel member on Flat Earth Debates on Nathan Oakley 1980 show. Go and check it out today. Subscribe, listen, keep up to date with the Flat Earth Debate. It is a daily debate. Anyone is welcome to come in. Nobody is restricted. Globe believers, if you think you've got proof of the globe, go in and state your case. 10th man's there. If you want to talk to 10th man about the sextant, if you want to talk about dip correction and how it won't destroy a heliocentric model, that's where you need to go. They are on the cutting edge, the tip of the spear, the cutting edge of flat Earth. The most advanced arguments. That's where this argument comes from, measuring a geometric flat plane. Once again, if you feel like the world turns on you, turn to Flat Earth School. It is around us 24/7 since the beginning of existence. Thank you for being here today. I hope you enjoyed this presentation. And join me tomorrow with Brian's logic. Until tomorrow, always get out there and just experience your Flat Earth School. Love to everyone.